Up until now, we've been talking about Ohm's law. We've been talking about the constitutive relationships between capacitors and inductors. And that's led us up to the early 1800s. By the late 1800s, the Industrial Revolution is well underway. We've got power lines that are beginning to crisscross America. And the power lines transmit a signal that looks like this. Of course, we know it's not just one, it's 120. It works out to be 120 volts cosine of 2 pi 60 hertz times t. And if you take a look at these power lines, the power lines, they're very long, so they look like inductors. And of course, anytime you've got a long line, you've also got some sort of non-zero resistance in the line. But they're made physically out of two long conductors that are hung relatively close to each other. You don't see two totally separate power lines in different areas. You see one power line with two wires running next to them. So those two long conductors separated by a dielectric in between look like a capacitor. And that might be a good representation of a mile of parallel lines. So the next mile might look like another set of resistors, inductors with a coupled capacitor. And now you've got a model of, say, 2 miles of power lines, and you're already up to a 1, 2, 3, 4, 5, 6th order circuit. So you can see the problem. If you want to come up with a good model of what goes on with 100 miles of power lines, you're looking at a 300th order circuit. Can you imagine how complex that would be? Just solving the initial conditions would be horrendous. Every new order adds an extra derivative onto the initial conditions. You'd be taking, the 299th derivatives it would be horrible. But there are some things that make this easier. Where does this begin? What time? When we studied first and second order circuits, we had some sort of switch or U of t that changed something at time equals 0. When does this change? When does it begin?
I guess it would begin, we'd assume, at like negative infinity.
Exactly. And because it's always been going since time negative infinity, any kind of initial conditions have long since settled out way back at also negative infinity. So in some ways, this is, in some ways, it looks a lot harder than what we've done, but in some ways it's easier because there's no initial conditions.
How can it not be
been on forever?
I thought, how can there not be initial conditions for this? I mean, you could just say that the inductors are essentially short and the capacitors are open.
No, you can't say that because conductors are only short in the DC world, and there's never a DC. It switched from DC to this AC source back at time negative infinity. And so any of those initial transients would have died out at time equals negative infinity. And now we're at some sort of steady state, but we're not at DC steady state, where inductors look like shorts and capacitors look like opens. We're now at sinusoidal steady state. So we'll write this new idea that we're at sinusoidal.
So yeah, because the previous sections were about taking
steady state.
So the previous sections were about taking, I guess, sinusoidal circuitry and turning them into DC steady states. This one, we're just embracing the sinusoidal aspect entirely.
Exactly. We're saying that we're in this new thing that we haven't looked at before called sinusoidal steady state. We've been in sinusoidal steady state forever, and we will be in sinusoidal steady state forever. And we just need to figure out what that steady state is. That's exactly right, Kyle. Okay. So if we were taking a look at it from a differential equation standpoint, there is only a forced solution part. There's no natural solution. That natural solution would have decayed away long ago. And that brings us to phasors.